So today the topics we're going to talk about is the network and bandwidth network Kubernetes clusters. So thank you very much for being here to listen to our demo. So I would like to do self-introduction first. My name is Yifeng. I come from VMware, and now I am doing the PKS and stability testing. And before that, I'm working for the VMware integrated container, and I also help to develop the VMware integrated OpenStack and VMware big data extension. And then I provide system tax development. Hi, my name is Yifeng. I also come from VMware's China R&D and the Beijing office. So what I do is I work on VMware Kubernetes products, and I do a lot of Kubernetes. And before that, I've actually focused on nutrient OpenStack networking. So it's quite related to networking. So if you have any questions or if you have any topics related to networking, do not be hesitant to talk with me. So for our today's agenda, I'm going to talk about Kubernetes, the components, and the standard schedulers, as well as the quality of the service and some of the network features of Kubernetes. And then also we're going to talk about how to enable network and bandwidth codes. We all know Kubernetes. It is the de facto standard of containerized application. I already list a lot of the advantages of the Kubernetes. In terms of the scalability, it can reach to 5,000 nodes and 300,000 containers, and the number keeps increasing, and also it can provide separations of the resources, so it can easily realize the multi-tenant application, and also no matter it's public in the cloud or it's private in the cloud or other different environments, and they all choose Kubernetes because the option is not quite wide range, and you can easily realize the immigration. So here are the major components of the Kubernetes that we have: container runtimes, and which is mainly focused on Dockers, and Kubernetes. Kubernetes is a component that manage the pod, and SCD is the database, and so all the objects were stored in this SCD, and API servers is actually one of the interface for the objects, and for the scheduler, Kubernetes scheduler is actually the tool to schedule working load as an appropriate nodes and controller manager, and is the management of the tools for the life cycle of controller, and KubeProxy is a component to manage the networks and IP provider. It is then level 2, level 3 and class communication and the network policies and the coordinates is actually the domains server. And let's first of all look at Kubernetes standard scheduler. Also, you can see from this slide, and this chart shows that how Kubernetes choose the node for pods and how to do the scheduling. So first of all, and there were a series of filter rules. So the purpose is to filter out the inappropriate nodes. So here I've listed 3 volume filters. So that is to say your port do have some requirements on the volume. So if the ports couldn't match with the volume, or it is not in the same zone, the node will be filtered out. So there is actually a candidate list. So the inappropriate node will be filtered out of this candidates in the list. And the second is the CPU and the memory. So if there is no sufficient CPU or memory, and the node will be filtered out. And then also for the specific nodes, and then probably the certain problem need the label. So if there is no node matching label, the node will be filtered out. And the second step is the rest node will be scored and ranked. And so there were several follows to follow. The first one is the node replicas distribution, whether it's even or not. And another ranking principle is the utilization of the node, and also we need to check whether the resource usage is balanced or not. And another noding principle is the affinity and the tenant priority. And then the highest ranking node will be selected, and the partner will be deployed on that. And in Kubernetes, there are three the quality of the service and classes. The first one is the guaranteed. Guaranteed means when request is equals to the limit, and then we'll all set it up, and this resource will be appointed with the highest priority. And the second class is burstable. So that means you're already filling the request limit. However, your request is smaller than the limit, so your resource will not be beyond the limit. And the last type is the best effort. That means you didn't fill in any request, so it can only guarantee the residual resources that being deployed. And for the quality of the service, in the standard Kubernetes, the QoS only considers CPU and the memory. And here are several bandwidth-sensitive applications. For example, audio, video, IP telephones, web applications, emails, and also online gaming, as well as file servers and P2P. So for all of these applications, and we have to deploy it on the node that with the sufficient bandwidth. We also have to guarantee the very low network latencies and very high traffic passed away. And as my colleagues just mentioned, that there were some sensitive applications to the bandwidth, and for example, some telecommunications applications. And also we have to consider that in the current community of Kubernetes, there is no open and complicated solutions upstream to the cluster. So let's review a little bit what is the current network feature of Kubernetes. The first one, and I think you're familiar with that, is the CNI plugin. And it is a kind of Kubernetes add-on, including Flatnon, Calico, and Marcus, and while with the CNI Genius, and they can be seen as a kind of the CNI add-on. So the CNI plugin actually provides the layer 2 and layer 3 connectivity. So many CNI plugin can provide the native ingress. So you can actually define the ingress by yourself natively, and so the CNI plugin is going to point it your ingress to the end point, and to identify the responding port. And also the community has been talking about the multi-NNS support, and for Meta's the CNI Genius, which is provided by Huawei and Intel's Maltus, and as well as network service mesh, and all of these tools can help us to solve the multiple NIC features. And because by default, we know that the CNI only have one NICs. However, with this new types of the CNI plugin, we can support multiple NICs. And also for the native, we have the network policy, so which can help us to define the network policy resource and to provide the macro segmentation for ports. And another one is also frequently seen is the service mesh. It can provide the 7 layers service bus and mesh. So here are some and most frequently seen network features in Kubernetes community. And however, we don't really have no research for things like network queues. On the other hand, and in the virtualized infrastructures, we already solve the problems of network performance. For example, we can use the PCI pass-through and to pass through and the hardware on the host, and also we can use the SR-IOV and to do some improvements with the network performance, and we can also use virtual switch hardware acceleration to help us to improve the network performance. And similarly for VM, if we want to solve this issue, we have to run the applications within the container, and we have to have the same considerations. So the basic discussions in our community are actually in two tools. The first solution is the device plugin, and if you check the Intel and their bottom layers developments, they talking about DK plugin, they talk about the GPU plugin. So those are all device plugins that aimed to allow the pod to use the hardware resources. So if we want to improve the network performance, this is actually the solutions that we can consider. Device plugin can actually match the hardware resources with container. And another way is the magnet VLAN, and we can actually let the pod to leverage the host of the containers and directly use is the IC. So those are just some discussions in our communities. However, we are going to propose another solution, which is listed on the previous slides. And the network queues requirements is our recommendation. We think that by using this way, we can actually provide sufficient network solution for ports from different or from a more comprehensive dimension. And as Yuyang just mentioned, within the community, and there were already several network features, for example, hardware accelerations and different solutions to improve the performance. And so today, I wanted to talk about using another way to improve the network QoS. So we need to make Kubernetes smarter. So what we can do are two things. The first thing we need to do is traffic shaping. So that means on each worker node, we have to reserve the sufficient network bandwidth, sufficient resources for it. And also we need to do ingress and egress controls on the pod. And the ingress is the feeding, and the egress is the output. And also in terms of Kubernetes calculations, we also need to take the network resource into the consideration. So the prioritizer and the filter is going to be considered during the calculation. And on the physical level, the BareMetal deployment, and as you can see, we already have quite fixed physical IC. So since the bandwidth is quite fixed, we do not need to reserve any other extra spaces. And however, we need to conduct the ingress-egress control on the pod. And we already have Linux traffic control, which is actually the tree-shaped queue. So this is actually the NIC. So for each granting pod, and there is a branch, and each burstable pod have a branch. So the best effort pod and is shared with one branch. And so with the scheduling and the deployment, and it's going to issued and it's going issues guarantees. And so the guaranteed in the pod is going to deploy according to the request to guarantees that all traffic will be sent out. And for the burstable pods, and since the request is smaller than the limit, and so they want to guarantee that the request will be satisfied. However, the gap between the request and the limits is really depends on the residue bandwidth. And then it's going to issue the rest ones on each branches.
So this is from the rest of the tokens. And when they are idled, those traffic can go out. So in the watch node deployment, most of them are in the VM. So on this slide, vSphere plus NSXT, you can see the Kubernetes architecture. Here, this is the master nodes, and you can see NSX and CP, and it will constantly watch or observe Kubernetes objects, and it will also connect to the pod through NSX, MP, and CCP, and to set up the fireworks. And in the worker node, you can see we can manage the traffic, but the management traffic and the data traffic are separate. All of the pods have been connected to OVS, and there is a specific network card connecting the OVS with an VDS. So with this kind of architecture, on the network card, you can manage the traffic, or you can connect the pods with the virtual bridges, and then you can manage the traffic of those connected pods. And the core principle for us is to manage the bandwidth of the node and the ingress and egress bandwidth of the node. For example, when a user is requesting a pod from the CPU memories, in the metadata, he or she can add something about the bandwidth he or she needs. And then with the scheduler, the pod can find the scheduler extender. And first, the nodes with unavailable resources will be excluded, and the rest part of the nodes will be scored, and then we can select the nodes with the highest score, and then we can bind the pod to it, and then the NSX node agent will watch the switch, and then NSX will register the pod, and it will tell the pod how much bandwidth it needs, and then reserve the bandwidth in the watch switch. So on this node, you can see the user had selected the 2G bandwidth nodes, and there are already 2 pods existing on it, and we can have a 900 megabps, and there is still 1300 megabps. And this is about the detailed steps. The first step, on the workload, you need to reserve sufficient bandwidth. With NSX feature, that is I/O control, we can set the same share for each of the nodes. And share means priority weight. When there is a traffic jam in the network, you need to think about who is of the better priority. And in the virtualization or in the cloud, it's not about the running of the Kubernetes. It's also about the running of the other applications. So there is a problem of the weight. And reservation and limit should be set in the same value. And then we can guarantee that we can reserve the same bandwidth. And in the nodes, we should add a label to illustrate that this node can support what amount of the maximum bandwidth. The reason for us to list the class API on this slide is just as my colleague had mentioned, we can have the automated result. And one of the ways is that with the NSXT and NOC, we can control the bandwidth. But who will help the cluster to perceive that there is a request for reserved bandwidth? One option is to use the cluster API. Just as we had introduced in the morning, there is a management cluster API which had been running an add-on, that is the cluster API control plane. And then you can define what the clusters look like based on different cloud providers. And in these providers, we can define the bandwidth. And then it means that on the GCP or GKE, there is a definition. There is a profile for each of the workload, that is the memory of the CPU. And now you can extend the bandwidth. So with this kind of the mechanism, the Kubernetes cluster, which is running on the VM, can be made into what you have been desiring. And this is also about the bandwidth. And this is a screenshot of a part of how to define the workload provider, and there is a property about the bandwidth. When you have a dedicated bandwidth, then the cloud provider, such as the vSphere provider, can perceive that there is a bandwidth property, and then we will call the relevant interface, and then the VM can be set into specific bandwidth. So this is about the steps of setting a fixed bandwidth, and Yifeng had just explained to you the principles. Now, Cluster API is mainly for the purpose of automation, and this is a new project set up for the automation. And with the Cluster API, you can better set those figures, but of course you can do it manually. Just as my colleague had mentioned, you can set them manually. And now what we need to do is that after labeling those nodes, and then you need to apply for the pods, and you need to tell the scheduler how much resources, network resources specifically you need. And here we had listed the ingress bandwidth and ingress bandwidth burst, as well as the egress bandwidth and the egress bandwidth burst. And cost is about priority. When there is a traffic jam in the network, whose package would be output first? And next, we need to extend the Kubernetes scheduler. Kubernetes allows the extension of the standard scheduler with additional filter and prioritize rules. This is the external UI. Maybe the Kubernetes scheduler will schedule this. First the filter, and then the priority, and then you can see the weight here. From this slide, you can see that there is a chain on the filters. Step by step, you can exclude the unnecessary node. And I had just introduced 3 default filters And if you want to extend Kubernetes, then it will schedule the external filter to continue filtering. After the filtering, we will have the prioritization, and in each of the box, you can see the rules, and the final score is add up of each of the separate scores, and it will also schedule some of the external prioritized rules. About algorithm for extended rules. First, you need to calculate the capacity of the node. And just now, we have the labeled bandwidth, and then we should multiply it by 75%. And this is the best practice recommended by NSX. And we need to know about the required or requested capacity for the new pod. And this is the maximum value of the ingress bandwidth bus or the egress bandwidth bus. And for the rest of the capacities, we should use the total node capacity to minus the existing pod's capacity, and then the minus the new pod request. So you need to check the value. If it is smaller than 0, it means that we have insufficient resource, and then you need to remove this from the candidate list. If it is equal or larger than 0, you can remain this pod in this node. And then about the prioritized rules or priority scores, you need to use the node capacity to minus the sum of the bandwidth request, and then to divide it by the node capacity, and then to multiply it by the weight. The more the remaining resources, the higher the priority score will be. So these are quite straightforward rules, but we, of course, can add some more complicated and scenario-based rules. Here we have listed a case. For example, there is a newly requested pod, and it requests 600 Mbps bandwidth, and there are 4 nodes in this cluster. And node 1, well, we didn't label one of the nodes, and 3 of the nodes have been labeled. All of them have the 1000 Mbps capacity, and in node 1, 300 Mbps had been consumed. In node 2, 500 Mbps had been consumed, and in node 4, there's no pod running in it. And after the first round of the filter, the second and the third node should be removed, because node 3 does not have any reservation of the bandwidth, and node 2, it is exceeding 1000 Mbps, 500 plus 600, or it is larger than 1000, and then we need to score them. The higher the remaining resources, the higher the score would be. So node 1, the rest is 700, and node 4, the rest is 1000, so node 4 will have the highest score, and multiplied by the weight, it has a score 4, and node 1 only have 1. So finally, we would select node 4 to place the pod. And these are some of the figures based on our research. If you don't manage the traffic for the pod, then the result is unanticipatable. So maybe the key task had its traffic occupied by some of the other unimportant node. And on the right-hand side, in the spec of the pod, I had defined the bandwidth needed, and this is in line with requested bandwidth. And the blue line shows 100 Mbps, and the orange one shows 50 Mbps. So this is our presentation. Thank you. Do you have any questions? We had done something similar before, and we had some other shared resources which cannot be isolated. And I have several questions. The first one is that we are using the scheduler extension function, right? But actually, we also have the multiple scheduler framework. And can we consider of using that? Yes, there are two options. The first is that when you have been starting the schedulers, you can define the policy, and then you can add some rules based on the default rules. And the second option is to set up multiple schedulers. And when you created those pods, you can dedicate which scheduler to be used. And because of the resource of the network bandwidth is more similar to CPU because this is compressible, and for some of the guarantee pod, you have allocated the reserved bandwidth. If the pod is not occupying this bandwidth, will it be released temporarily? Yes, it will be released. You're completely right, because this is compressible. There's another question.
I couldn't remember my question, so that's it. Thank you. You just mentioned the compressible, and however, in your chart, you actually filtered it out with which slice. I mean, when you are applying them, the 500 and the 600 one. So this is the node 2, right? And so on the first time, you actually filtered it out, so it will not be allocated. So your request value, I mean, you already filtered it out for this node. So that means if it is just a request, and then you cannot really, after you filter it out, and you cannot really guarantee the compressibility. I mean, the total bandwidth is the 1000, so that you actually calculate it according to this the request of this node. Well, just as he just mentioned that our bandwidth is compressible. So when you are creating a pod, and when you are doing a pod request, you have to guarantee. For example, in this case, it's the 600, and however, when you are actually running within the pod, and you are running it at a very low workload, so your network traffic is less than 600. So we are doing that because we want to guarantee the performance. And when you are doing this request, we want to satisfy your request. And I cannot compress here without understanding or without knowing that when will be the peak traffic times. So if we only deploy it according to the compressed level, I cannot make sure that for another pod during the peak time, I cannot really make sure the performance of another pod. So what we do here is I probably may have some idle bandwidth, and even I have no idle bandwidth, I cannot give the total bandwidth that is higher than the request. So you actually calculate it according to the minimum value. Yes, the total bandwidth that adding all the pods together will be not really smaller than our ceiling. So that means I cannot schedule another pod, and if I cannot make sure that I can guarantee your reservation. So this is the solution. This is strategy we take. Hi, hello. So, and I think the question they're asking is very reasonable. And you said that you want to provide a guarantee for all the nodes. You said it's quite intuitive. And so when you actually provide the residue of the adult bandwidth, do you think that this kind of strategy is very conservative? So will you actually consider like a smarter or more aggressive strategy? Yes, I mean we are still thinking about are there any smarter solutions. By far, I couldn't tell you that I can find another smarter resolution, because if you guarantee, then you probably need to consider your burstable and the best ever. I mean, if I can make the resource and the allocations really dynamic and smarter, and then that is really good. But by far, there is no way for us, I mean, not yet, for us to find a better way. So basically, this is our solution, our current solution, because for our presentation, you already saw that on our pod is actually on the interface of an OpenStack, and this is actually on see, and for this I see we can reserve some traffic, but I cannot guarantee that all the workers and the workers in the interface and will have a fixed traffic guarantee. Yes, I totally understand. I'm just very curious because when you are making and your request, and when you identify your request, we all know that for calls container it's changing a lot and it's keep changing all the times. And so since I do not really know your workload, and I don't know that for your historical data it can be used as a threshold, or I don't know whether you have considered to use them as a way of training. Well, yeah, I mean, yeah, I agree. Probably I can develop a very smart algorithm, and so I can train it, use it to do the training. Yes, I mean, you can probably check your historical data of your BareMetal deployment. Yeah, I agree with you. We actually considered this kind of an approach, so probably we can use some very smart AI algorithm, and so maybe not for the application of the networking, but we actually try to use the algorithms and to be used on the public cloud. And we've actually tried the CPU memory estimation, and there were a lot of similar algorithms, but if we can apply this kind of algorithms in this kind of bandwidth domain, because by far we know that bandwidth is very, very big. It is about hundreds of thousands and megabytes. However, I don't know. I'm not really sure whether it is feasible or whether it is meaningful for us to use the AI algorithm to estimate the allocation of the bandwidth. I mean, by far it's not necessary. However, the algorithm really can be used with the CPU AI algorithm. Well, I think that is a very good topic. Probably we can discuss this later. And for the compressible question you just asked, if you've actually allocate the difference in the traffic. I mean, for the guaranteed, there is no. I mean, you do not need to send any or allocate any traffic for them. You can actually provide those traffic through our code. Thank you very much. Thank you very much for participating in our demo.